Welcome to the Atocan. We are in the middle of the Amazon forest in Brazil, and this is a scientific camp here where many people from different countries work. We are now here with a big group from the Netherlands, also some German people and many Brazilians. The Amazon is a very important ecosystem here, and this is built in a natural reserve where only scientists and people that live here anyway can come, but you cannot enter it otherwise. And this is to do research about the role of the Amazon forest for the global climate system.
We are 8 hours from Manaus. It's, I think, on a straight line, and I think it's not so far away, but we are in a pristine environment that has been not touched by the human beings. And it's an environment that already, and I just came back from the trekking, we think that the green ocean, as we call it, the Amazon, is totally homogeneous, but it's topographic change, and already very close to the atoll. This is an excellent facility with these 3 towers that I mentioned. We have another site that is 5 kilometers south with a completely different conditions, and there we are measuring clouds.
What we are doing here is characterize really the boundary condition, especially on the vegetation. So how the presence of the vegetation and the conditions of the vegetation are affecting the above atmosphere. And then it also comes into the part of the clouds. So if we have clouds on top, there are changes in radiation that also affect how the plants are doing photosynthesis, for instance.
A basic need of a plant to photosynthesize and thereby contribute to the exchange of water, CO2 with the atmosphere is this amount of light that it receives. So this depends on how high up in the canopy you are, how much you see the sun, quote unquote. But it also depends on everything that happens above the canopy. So how much you see the sun also depends on whether a cloud passes by or not. What is a radiometer? That's essentially just a measurement device, a little box with a sensor on top of it that measures radiation. It also measures how that radiation distributes over the different wavelengths of the visible light spectrum. It might be so that plants can only use certain parts of that spectrum for processes that are useful to them, like photosynthesis.
They are picking leaves for us, so we ask them a leaf and quickly we take it to the instrument because otherwise the stomata of the plant start closing.
You expose the leaf to light, CO2 and humidity conditions inside the chamber, which you can use to mimic the conditions that the leaf sees in the canopy. So for our measurement approach, we pick leaves from different layers in the canopy. We transport them very quickly to the leaf chamber, so fast that the leaf has not had time to adapt to the conditions here. We set the conditions to reflect the conditions in the tower, and then we measure what is the photosynthesis and the transpiration and the stomatoconductance, what the leaf would have had when it would be still in the forest at a specific height. And these measurements then tell us how the vegetation is influencing the atmosphere. For each leaf, we then get 2 measurements. One representative measurement and one measurement indicating the maximum photosynthesis rate for that specific leaf. We don't know yet if the vegetation is much different at the surface, at the top and somewhere in between. So we collect the data on the 3 levels. And the parameters we get from here we can put in a model, and then the model can be better to represent what is the gas exchange of the whole forest.
I'm collecting leaf samples from different heights of the canopy to measure the water acid composition out of the leaf. We just take from shade or from light different compositions, so to understand like the water isotope composition in the atmosphere, so that we correlate with the gradient water vapor measurements that are installed in the tower. So I have to keep them cold enough, otherwise the water will escape, so then the measurement will be biased otherwise. Yeah, the root of the cloud we think is just leaf. So then that means like the leaf water. So that's what we are looking for. Leaves.
So we are here in situ to learn, but mainly, is to quantify the biology, the chemistry and the atmosphere, with the main goal to see how vegetation is related to the cloud formation and intensification.
The type of weather that we have here in this time of the year organizes in what we call shallow cumulus cloud fields, where you have these little blobs of cotton in the sky that pass over the surface that create a random pattern of shading. In a second, you go from shaded to sunlit or vice versa, and that lasts for a couple of minutes, and then light comes back on or shade will arrive. The way this affects the atmosphere is non-linear, so that by just averaging clouds and no clouds is something different than actually describing a surface where part is clouded and shaded and other parts are sunlit. One instrument that we brought here to measure these exchanges at the surface of CO2, water vapor and heat over very short time periods is a scintillometer. It's an instrument that consists of a transmitter and a receiver. And it measures the intensity of the scintillation effect in the atmosphere. And that's the effect that on a very dry, hot day you can even see with your naked eye. It's when over a tarmac road you see the air like dancing, and that's the scintillation effect. And intuitively you can already feel that the stronger this effect, the more heat there's being transported. Another thing that we're going to try to do with this scintillation technique is to combine it with measurements from our colleagues from the University of Utrecht, who measure isotope concentrations of CO2 and water vapor. And the novelty there is that they do this very fast. That's new, so that fast enough that we can determine the fluctuations brought about by the turbulent transport. And if it's going to work, we don't know, because this has never been done.
Our research question is to better understand the exchange of water vapor and CO2 between the land surface and the atmosphere. And we do this with isotopes, and this helps us partition between evaporation or transpiration from plants. So we are going to investigate the water vapor and CO2 molecules. We have two laser spectrometers, and they use a light beam at a certain frequency which gets absorbed by these specific molecules. It's so specific that it can even distinguish the absorption taking place by a light molecule compared to one that has one heavy atom. We're going to compare their heavy and lighter isotopes with each other, because certain processes in the environment change the ratio of heavy to light. This is what we're after.
So we see this as a loop between vegetation controlling moisture and heat transport to the cloud base, and the clouds are also influencing by changing radiation and thermodynamic characteristics. This is a perfect natural laboratory to study how the system is interacting.